So, first of all, I would like the organizers of HHH give me the opportunity to give this talk. It's joint work with Ralph Kaufmann of Purdue University. And so it will be a quite categorical talk. So I will begin with some topology and hopefully end with some topology, but in between there will be a lot of category theory and actually combinatorics of graphs. So I hope it will be interesting. Nonetheless, the plan is the following. I will begin with an outline. Then I will talk about Feynman categories. And operads. Then I will talk about cyclic and modular operads. And at the end, about derived modular operads. So, let's begin. It's a small outline of what I want to prove, or at least a sketch a proof of it. So it's about combinatorial models of moduli spaces. So what is well known are moduli spaces of Riemann surfaces genus G with n punctures. So, for short, I won't give a precise definition of this. It is a quotient of the Teichmüller space by the mapping class group. And I will assume that the Euler characteristic is negative. So say you have a surface of genus G with n punctures, and so the Euler characteristic is 2 minus 2G plus n, and this should be negative. And then, you can think of the Teichmüller space of the space of hyperbolic metrics on this surface up to isotopy. And the mapping class group is the group of isotopy classes of different morphisms which preserve the orientation and are relative to the n punctures. So and you take the quotient, and so somehow these are equivalence classes of hyperbolic metrics, and you want to understand the topology of this space, and there are So big literature on it, and especially what I'm interested in is the relationship with Riemann graphs. So there is a well-known theorem, so which goes back, I think, to Mumford, Harrer, and Penner, which says that this space is actually homotopy equivalent to a space of metric Riemann graphs. So there's this even besides a statement. So if you add some weights for the punctures, positive weights, then you get a space which is homeomorphic to the space of metric Riemann graphs, which satisfy a certain stability condition. So this stability condition, this means two things. So it means that the first thing is the fact that the Euler characteristic must be negative, and the second thing is that the Riemann graph should be at least trivalent. So each vertex. So
How does G and N come up in the graphs?
I will explain it. But it is a Riemann graph has a local cyclic structure, and you can define boundary cycles. And the number of boundary cycles and what I call the combinatorial genus, this is just the rank of the fundamental group, together determine the geometric genus. And the n is actually the number of boundary cycles. So both are determined by the Riemann graph.
Yes, you need n to be at least 1.
Okay. Yes.
How do the graph depend on p and n?
And that is the
It's the
same
same
question.
question,
Yeah. That's so. But I will come back to this at the end of my talk. I just I'm interested in an extension of this to the bordered case. So I will introduce moduli spaces where you have more numerical invariance, like this. So this is moduli space of Riemann surfaces of genus G is S functions, and new boundaries, and each of the boundaries contains marked points, and the number of these marked points are given by these numbers. So that's the moduli space I'm interested in, and there is an extension of this well-known theorem which also works with Riemann graphs, but slightly more general Riemann graphs. So it's not so easy to find actually the literature on this. So I think there is a paper by Penner which treats the case P1 equals P2 equals P nu equals 1. And there is a paper of Kaufmann and Penner where they treat the general case. And so it says that this space is homotopy equivalent to a space of metric ribbon graphs. But now I allow external flags. So normally a graph, so for instance this is an example of a ribbon graph where you have cyclic orientations around each vertex. And now I allow also flags, external flags, which are just half edges. So edges which are without vertices. So each edge, one should think of it as a composed of two half edges, which are related to each other by an involution. And these are just half edges, which are, if you want, fixed points under the involution. So here you have metric ribbon graphs with external flags. And otherwise, it's the same. They are stable, which means that the Euler characteristic is negative, and at least trilines. Triline. How do you pronounce triline? Trilane. Okay.
Do we not require the weightings on this one? The weightings you had on the first one, not the second.
So here the weightings actually, these numbers, how they are related to the graphs. You have, again, if you have external flags, you have your boundary cycles. So here, you see you have actually 3 boundary cycles. So let me perhaps, in order to get it more interesting, put the flag here. So you have again 3 boundary cycles. So so for instance, you can go, if you start here with this half edge, you get this, and this, and this. This is one. And here you get this. This is another one. And the outer one is this one. And the flags give markings on this. So here you have 2 markings, and here you have 1, and here you have none. So this means that you have 1 puncture. So here S is 1. You have mu is 2. You have 2 boundary cycles with markings. And so if you call this pi 1, it's 1, and the other one, the pi 2, is 2. So these are the ribbon graphs which are there. And so the theorem I would like to explain a little bit in my talk. So this is joint work in progress. So with Kaufmann. It's actually a very algebraic way to get these homotopy types. To some extent it is a homotopy characterization of these spaces. So I will explain what it means, but you have the notion of cyclic operad, and there is a notion which less symmetries, so which we call planar cyclic operads. And there is a notion of modular operad, and again a restricted version of it with less symmetries we call surface modular operads. And there is an adjoint pair of functors. So I call this G tilde and G tilde upper star. So this is a forgetful functor and this is the left adjoint. And the theorem is that if you take the left derived functor of this, of the terminal planar cyclic operad, then you get a surface modular operad, and so the arities of modular operads are just given by genus and a degree, so it's Gn. Surface modular operads, the arities are precisely given by these by this kind of numerical invariance. So if you evaluate it on just, this is actually a topological type if you want. It is a topological, it's a closed surface with S functions and new boundaries which are marked respectively by pi points. So if you evaluate it on this arity, then up to homotopy you get precisely the modular space. So it is some kind of very algebraic construction of these homotopy types. And so this theorem is very closely related to the theorem of Kevin-Costello, which is some kind of DG version of it, but where you erase this planar surface. So if you erase it, then what you have to do is, instead of taking the terminal planar cyclic operad, you have to take a cyclic operad for planar structures. And then this theorem is more or less stated by Kevin-Costello, but not in the realm of spaces, but rather in the realm of DG, of differential grading modules. And so there is also a paper of Jeffrey Jan-Siracusa, I think it's 2011, where result very much of this type is stated. So I think so this is some kind of DG version, and here what is a little bit, I would say, sketchy in this paper is the definition of cyclic operad and modular operad. He somehow proposes a definition, but he just, I think it's not 100% correct, and it is, so I would say you can also interpret this as a task of making Jeffrey's article completely correct. Because there are a lot of calculations which are very close to what we are computing. Just the formalism is different. And the formalism, so which I would like to explain a little bit, is the formalism of Feynman categories. So Feynman categories.
Could you say something more about the, you've got an equivalence there. Could you just say something more about the left-hand side? What does it mean?
So the left-hand side means that you take the terminal planar cyclic operad, and here you take the left-derived functor of this. So I will give more details of this. Actually, there is a W construction applied to the terminal, and then you apply this functor. And you get the surface modular operad, and the arities of these operads are precisely these things. And you evaluate. And somehow this tells you that these spaces form a surface modular operad. And the operations are given by gluing and self-gluing. And it's along the marked points of the boundary.
Will you be telling us what a surface modular operator
Yes, yes, that's the end of my talk. So finding categories.
Maybe coming back to John's question.
Yeah.
So I certainly do understand the right hand side, at least to some extent. This modular space, it's interesting, you want to compute it. Does the left hand side now, being algebraic, allow you to compute it or just detect further structure as you said it's then?
It can be computed, yes, yes. Yeah. And actually somehow what I just showed that this space is actually the realization of a certain category of reading graphs, and you can show that it is equivalent to metric reading graphs. That's the proof, more or less. So, but you can.
So you go through the
exactly.
Kaufmann planar results.
Yeah. But you get these categories somehow formally. So these Feynman categories were, there is a asterisk which appeared last year from, so written by Kaufmann as well. Okay, so let's try to come to Feynman categories. So what I will do is I will first give the classical definition of what is a symmetric operad, and then try how you can express it in the world of Feynman categories, and then this gives you a way of defining all the other types of operads. So a symmetric operad is given by a family of objects indexed by the natural numbers with some action of the symmetric groups and composition maps which a unit which satisfies some equivalence and associativity conditions. So the idea is, and this idea is also quite classical, is to understand these operations as trees, or actually corollas. So for instance, you present a three-ary operation by a rooted corolla, and then you present compositions of operations by gluing of corollas. So for instance, take an operation of arity 3 and put into it operations of arity 1, 2, 1, and 3. Then you can just plug these corollas on the top of the heading corolla, and you can contract these inner edges, and this gives you an operation, so which is given by this composition map. Which now has 2 plus 1 plus 3, so 6 inputs. Okay, so geometrically or combinatorially, these compositions are given by gluing of rooted corollas together with contraction of inner edges. So gluing plus edge contraction.
But you have to contract all inner edges simultaneously.
Yes, yes. So now I define the Feynman category which is associated to the family of symmetric operads. So the objects of these Feynman categories are disjoint unions of rooted corollas and the morphisms are now also graphs. Actually, the morphisms are disjoint unions of rooted trees. So I have to explain what are source and target of a rooted tree. So, and I
use Feynman category in plural. Now you define a particular one.
exactly right. I define the Feynman category whose algebras or operads are symmetric operads.
But there are others. Which
There are others corresponding to other types of operads.
Exactly.
That's exactly what I mean. So, what are source and target of a disjoint union of rooted tree? So I can do it for a rooted tree, for a single rooted tree. You consider. So if I have a single rooted tree, like something like this. So the source. So the source is given by the corollas, which corresponds to the vertices. And so this is a disjoint union of corollas, which are also rooted.
Forgot one or
No, I forgot none, I think. Yes, I forgot one.
okay.
In fact, so you have, and they are all rooted because the root here gives a canonical root for all these corollas, and the target is given by the corolla you obtain when you contract all internal edges. So you contract all this. It's the corolla obtained by contracting internal edges. So this here we have 1, 2, 3, 4, 5. So what is left is what is in blue. So this is the target. And now how do you compose? So composition is given by insertion of trees into vertices. Composition is induced by inserting rooted trees into vertices of rooted trees. And this is possible. So here it is possible because you want the target of one of the morphisms gives you all these gives you a rooted corolla, and if this coincides with the corolla of a vertex, you can include the whole tree into this vertex. So say you have some other tree and here you have a vertex with 1, 2, 3, 4, 5 inputs, you can insert this tree into this vertex. And that's what gives the composition of the category. And now the proposition is that is twofold. The proposition is that so this defines this joint union defines a symmetric monoidal structure on this category, and strong symmetric monoidal functors of this category into any symmetric monoidal category are the same as symmetric operads in E. So now I give you the general definition of a Feynman category. So a Feynman category is given by a triple so F is a symmetric monoidal category nu is a subcategory which is a groupoid, or a subgroupoid, and this E tensor is an equivalence of symmetric monoidal categories between V tensors and the isomorphisms in F. So where V tensor is the free symmetric monoidal category or free permutative generated by V. So in our case of F-sim, these are just the corollas and the isomorphism between rooted corollas. So these are rooted corollas. And what is important is that you have also automorphisms. So this here gives you the symmetries of the arities. So say if you take such a rooted corolla, you get precisely the group on three. Symmetric group on 3 letters. Now, so those who know well colored operads, so one can show that there is a 2 equivalence between Feynman categories and colored symmetric operads in sets. And the colors are given by the objects of this V. So V is for vertex. And now I would like to just to give some kind of general picture.
What's the role of this I tensor?
I
mean,
if
So V
the
is
fact is that you somehow it gives if you have a disjoint union of corollas, then it's unordered. But you need to order them. So in this construction of the free permutative category on this, actually you define tacitly orderings on your corollas. And somehow what is important is that the isomorphisms in your category are compatible with these orderings. That's the. So somehow
is I tensor really a choice? I mean, V is inside F iso. F iso is permutative. So
yes, you can say
V tensor to F iso.
Yeah, you can say it's just a property.
It's a property. Okay.
It's a property, but then you have to use here not free permutative, but free symmetric monoidal category. So you have to use a bigger construction. Then it becomes a property. Okay, so I give some kind of, so here you have symmetric operads. And then there is a non-symmetric version of it, which are called non-symmetric operads. And here you just forget about the symmetric group actions. And so here I give the symmetry, so I give somehow the vertices with the symmetries. Here you have rooted corollas. And here for non-symmetric operads you have also rooted corollas, but with a planar structure. So planar rooted corollas. So this destroys any symmetries. Yes, it's me. Okay. Yes, I will make it here. Now, so this here defines F sim. This here is F non-sim. Now cyclic operads are defined like symmetric operads, but you don't make a difference between inputs and outputs. So you only have corollas here and no root. And so non-symmetric cyclic operads, I don't like this name, but in literature it is used. We call it planar cyclic. They have planar corollas as vertices. And you see, a planar rooted corolla has no symmetry, but a planar corolla has a cyclic group of symmetries. So here you have cyclic symmetry. So I will use symbols for the final categories. And now modular operads. Here instead you have also corollas, but they have a label. So genus labeled corollas. And then there you have surface modular operads. And so there are also labeled corollas, but the labeling is more complicated. So labeled corollas. And now there are also the morphisms. So here for symmetric operads, the morphisms are given by rooted trees. Here the morphisms are given by planar rooted trees. And here for cyclic operads, the morphisms are just given by trees. But you see the insertion process works exactly the same. And I unfortunately have no time to explain it in more detail, but a cyclic operad, you have gluing operations, which just corresponds to the fact that if you have two corollas, then you have to label somehow the edges, the half edges, and what you do is that you glue these two half edges together and then you contract. So this corresponds to this morphism corresponds to a tree. So this is normally in literature this operation. For modular operads, what is new is that you have not only trees as morphisms, but you have graphs. So here you have graphs. And so why do you have graphs? This is because you also allow self-gluing. And self-gluing means that you also allow these two to be glued, and if you glue them, then you get a loop and you can generate any graph. So the Feynman category for modular operads is based on graphs, but you have a genus labeling of the vertices. And the morphisms are subject to certain genus constraints. So, so for instance, I just give you an example to give you a flavor of what is a morphism. Say, so this is a morphism, then you have the source here is this, and this, and now you can yes, so they are different. So you can, for instance, have as here you can have say you can contract these two edges and yes, you can have, I think you can have this, and yes, so I'm sorry. And each of these vertices has a genus, so this is G1 and G2, and this here has also a genus which is G3, and what must be true is that this graph here, it has a combinatorial genus, so it's the rank of the fundamental group, so it's 1, and so the combinatorial genus is 1 here. And what must be true is that G1 plus G2 plus 1 is equals to G3. So in this way, you somehow you keep track of the graphs which occur as morphisms.
So the same graph somehow actually has several morphisms. Each time there is a matching
exactly.
relation of the gene general,
Yeah.
then this picture would be a morphism from the left to the right.
Exactly.
Yeah. But then they are really different because their morphism is different.
Yeah. So the morphism, you have really, to some extent, you must need source and target to label all the half edges of your graph, and then you have a one-to-one correspondence. So this gives you modular operads. So these both have been introduced by Kapranov and Getzler, and so here you have planar trees.
Question on this gives you modular operads. This and just as before this proposition, the functors from
Exactly.
this
From
the
this
category
final
is-
category, which is defined by this,
into
yeah,
something
exactly.
monoidal are just the
are just the modular operads.
operads
Yeah.
of a kind. Okay.
So here, as morphisms, you have planar trees, and here you have almost ribbon graphs. Right? So it's generalized ribbon graphs. So So the nice thing about finite categories is that you can really compute extension functors. So there is, we have these 6 yes. You have these 6 Feynman categories. You have forgetful functors here, and here also. And these are more inclusion functors. So each tree is a graph, and each written tree, so you have these functors here. So what I want to say, what is important is that for each of these Feynman functors you have an adjunction between the corresponding categories of operads. So let me call this I, J. Now, one can, so there is these forgetful functors here behave like a topological covering. Actually, you can recover these three Feynman categories out of these Feynman categories together with a certain operad of this type by Grothendieck deconstruction. So here it is the symmetric operad for associative monoids. So I call it tau, which to a rooted corolla associates the symmetric group of the inputs. And this is the same thing as a planar structure for such a rooted corolla. Here you have a very similar operad, which I call tau planar, which to an unrooted corolla associates its planar structures. And you see it has the same cardinality as this one, because a planar structure of a corolla with 4 legs is given by the symmetric groups on 3 letters. The cyclic permutations do not change the planar structure. So this here is more in bijection, and actually what is true is that if you restrict this cyclic operad, you get this symmetric operad. And this Feynman category can be thought of as a Grothendieck deconstruction of associated to the functor, which corresponds to T assoc. So this is Grothendieck deconstruction . This means that the fibers over each vertex here, a non-planar corolla, a planar corolla corresponds to a non-planar corolla together with a planar structure. The same thing for a planar, for an unrooted corolla. So this is Grothendieck deconstruction associated to this cyclic operad. So this is the cyclic operad of planar structures. Sometimes it is called the cyclic of sig-as. So this is the cyclic version of the operad for associator. It's the fact that this has actually a cyclic structure. And this here can be constructed by calculating the left Kahn extensions of this cyclic operad. So there is each functor of Feynman categories can be factorized canonically into a connected Feynman functor followed by a covering. So this Feynman category is really determined by this, and so is somehow can be formally constructed. And the fact that the arities here are precisely these topological types just means that actually this push forward, this left-hand extension of the cyclic operator of planar structures is given by these arities. Now, what about the modular? So this here, so the left-hand extension here is called the cyclic envelope, and the left-hand extension here is called the modular envelope. Now, the theorem I stated in the beginning is about the left derived extension for this functor, and this by definition is this functor applied to a cofibrant relation resolution of the terminal operad. And there is actually a canonical such cofibrant resolution, which is a generalization of the Borgmann-Vogt W construction. So Borgmann-Vogt W construction gives you cofibrant resolutions of symmetric operads, and for each Feynman category, so with a certain condition, so which is called cubical by Kaufmann. So for each cubical Feynman category, you have a W construction. So this, you can define it this way, and actually you can prove that in our case, this is homotopy equivalent to the nerve of the comma category over the object where you evaluate it. So say if you evaluate it on an arity, then it's homotopy equivalent to the nerve of this comma category. So, and this comma category is given by certain graphs, and the graphs must satisfy certain constraints, and the constraints is precisely are given on one hand by the fact that on the source you have only trees. So this gives you, for each vertex, and actually planar trees, gives you a cyclic structure, so a rhythm structure. So these the graphs here have a rhythm structure, and moreover, you have, so these arities give you exactly the external flags you must have, and the morphisms are given by edge contractions which preserve the rhythm structure, because it comes from this structure. So what you get here actually is the nerve of a category of rhythm graphs with external flags and S plus nu boundary cycles. And the morphisms are given by rhythm constructions. The morphisms are edge constructions preserving the rhythm structure. And Now there is, one can deduce from techniques of Ibusa in this, at the end of his book on Reidemeister-Torsion, that this category is actually homotopy equivalent to the category of metric Riemann graphs I mentioned in the beginning. Where metric Riemann graphs just means that each internal edge gets a length. And so this is known to be equivalent to the mapping to the moduli space of the same type. So this finishes my talk.
Questions for the speaker?
When you coined this name, someone surface modular opera, the surfaces are visible in this theorem. Are they also visible in the opera itself, or?
It is just because, yes, because the arities are given by these things here, which, so you can say for each closed oriented surface of genus G with S punctures and new boundary components which are marked, there is one arity, and the operad structure is given corresponds to gluing of these surfaces along the marked points. So for each such gluing, you must have an operation in your operad. So Martin in a recent paper calls them just non-sigma modular operads, but I don't like this name neither. So it is really for each topological, for each oriented surface of this type, you have an arity, and you have gluing operations for each gluing along marked points on the boundary. Yes?
If I remember correctly, in Chancellor Kusa's paper, there was some difficulty to do with the fact that in the penalty composition you're not allowed bivalent vertices. Whereas here you in principle
Yeah,
get
so this,
bivalent.
I didn't mention this, but I think the best thing to avoid this in the beginning is just to use non-unital versions of everything. So no units in the cyclic operads and in the modular operads, then you don't have bivalent vertices at all. But I think you can do it carefully and just show that it does not affect the homotopy type. But in order to get these classical models, they are at least trivalent. So
Yeah.
you have to show.
Was this designed to give you modular surface operads, or was it to just to understand better what they are?
So I think it depends on the authors. So for me, it was designed to understand better this, but I think for my co-author, Ralph Kaufmann, he has much more examples, different examples where you can apply the same technique and get yes, new surface modular operads.
So if I'm thinking about algebras for surface modular operads, should I be thinking of those as coming from physics?
Yes.
Always.